In June 2021, the European Commission launched a call to fund research ideas on emerging technologies for a zero-emissions future. A call to imagination, science, and action to develop technologies capable of reducing or removing greenhouse gases from our atmosphere. From all corners of the continent and beyond, ideas were submitted. Ambitious projects, technologies yet to be invented. 8 proposals were selected. 8 international teams, 8 objectives. This story is about one of them. The project aimed to develop a technology capable of continuously producing acetic acid or biomethane from CO2 captured in industrial processes or directly from the air using sunlight and microorganisms without consuming external energy or generating emissions or waste. This technology would help reduce the carbon footprint associated with the production of these compounds, which are widely used in the chemical and energy industries to make countless everyday products. The team from Uppsala University in Sweden had the mission of designing a series of organic photosynthesizers. These photosynthesizers must be capable of integrating effectively with the 2 distinct sets of microorganisms, those selected by the Institute of Chemistry at the Chinese Academy of Sciences for the production of acetic acid, and those identified by the Energy Technology Center in Germany for the generation of methane. The University of Amsterdam in the Netherlands was responsible for developing the reactor, a key component of the system, capable of operating continuously even under variable solar radiation, ensuring stability, efficiency, and compatibility with the microorganisms. From Spain, the Tecnalia team would work on the recovery and purification processes for the produced acetic acid, whilst aiming to minimize energy consumption. Meanwhile, the Swiss Federal Institute of Technology in Zurich would assess the environmental and economic impact of the technology, determining its future viability as a sustainable alternative. Idener, our Spanish coordinator, took on the vital task of bringing everyone together, ensuring alignment, momentum, and clear communication with the European Commission. But their role went far beyond coordination. They also developed a sophisticated mathematical model of the entire system, designed to simulate and optimize the reactor's performance under a range of conditions. This tool became essential in driving greater efficiency and unlocking the system's full potential. CINEA, also based in Spain, played a key role in connecting society with science, supporting researchers through impactful communication, fostering collaboration with external research groups, and championing the principles of open science throughout the project. The project's first major challenge was to identify the optimal organic photosynthesizers compatible with the selected microorganisms. These compounds needed to efficiently harvest sunlight, bind to the microbial surface, and transfer light energy with precision to drive the desired reactions. An equally critical challenge lay in achieving significant production of the target compounds, particularly biomethane and acetic acid. In this context, the use of archaea, methanosarcina barkeri, marked a bold and pioneering step, as it was the first time this microorganism had been paired with organic photosynthesizers for direct biomethane generation. This innovative approach brought not only exciting potential, but also a high degree of complexity and scientific uncertainty. As for the reactor, the key technical challenge was to design a system that could operate continuously, even as sunlight conditions changed. To meet this demand, a solar concentrator was integrated to harness and amplify daylight radiation, while solar panels and batteries were added to sustain operation at night or in low-light environments. Together, these elements ensured a stable and reliable system capable of running seamlessly throughout the entire cycle.
In Photo2Fuel, we use these type of devices which are called luminescent solar concentrators. And what it does is it takes broad daylight, which is transparent in this case. It falls onto the device itself, and then it's going to waveguide, absorb that energy and waveguide it to the reaction channels. And in this case, we made this reactor as a leaf because it's essentially doing the same thing as what an artificial leaf would do, is that you harvest energy somewhere and then you're going to convert the chemicals, in our case in Photo2Fuel, this is CO2, that you're going to transport through the veins of this leaf, so to say, and then convert it with the harvested energy from the sun that is perfectly matching with what we need into the channels to convert our chemicals.
The idea of the reactor for the Photo2Fuel is to have a control media for the bacteria to be stabilized with the temperature and the pressure and the atmosphere with the inlet of the CO2. This solution is going to be pumped in with a peristaltic pump into the reactor, and then it's going to flow in front of white light that simulates the conditions of the sun.
For months, the labs buzzed with activity. Cultures growing, reactions being analyzed, parallel trials, comparisons, constant adjustments. Light stayed on throughout the day and into the night. After nearly 2 years of dedicated work, the team reached a difficult conclusion. One of the two paths was no longer advancing. The biomethane system lacked stability. The microorganisms didn't respond as hoped. The results were too inconsistent. And despite tireless effort, this path appeared to be a dead end. For a research team, this is not a failure. It's part of the scientific process. Information gained here will form part of future successes. At the same time, the other path, the one leading to acetic acid, was beginning to show real promise.
我们需要一个非常匹配的美丽的一个电子转移的过程，因这个 biohybrid， 这个生物杂化的这个系统里面，我的理解是对的，是吧，田老师？
Production became measurable, consistent, and clearly capable of optimization. It was a hard decision to let go of one idea and commit fully to the one that was working. Because in the end, research also means knowing when to change direction. And at this turning point, the Photo2Fuel project found its true course. With the acetic acid pathway gaining momentum, the team focused all their energy on transforming a lab concept into a working prototype.
So here we have the prototype of the mini solar plant that we are going to use in the Photo2Fuel with red organic dye. So this will do basically the same, that we are going to emit the photons that is not absorbed by the bacteria in the red part of the spectra. In this reactor, we will going to couple a solar panel that will be located in the back of the reactor. So then all the photons that are not absorbed by the bacteria or by the organic dye are going to hit the solar panel, so then we can control all the electrical components as the peristaltic pump, the CO2 mass flow controller, or the heating for the reservoir. But also, we can couple high-power LEDs, so then we can control the reactivity also in the night shift.
It was vital that they built a system powered solely by sunlight, one that was self-sustaining and enabled the microorganisms to keep working uninterrupted day and night.
What I mean with self-sufficient is that you don't rely on the power grid anymore, so that you use solar panels to drive the pumps and that you use solar energy also to drive the chemistry. So everything is in that way relying on solar. And that you could say, okay, then at night, because there is no sun, well, you could supply it with some additional batteries there so that you have a little bit more power generation, so that you also at night can still power all the peripheral pumps and whatever, and that you then use LEDs to shine light onto the panels at night. So I think the combination in this way is that it's just like you could roll it out on a car, chariot, and in that way have it outside or out in the open to start producing chemicals. And so that can be deployed then anywhere, where there is in production facilities suited for that, or just at the home to make maybe a bit of methane or whatever you would need for cooking, for example.
That is how a small yet powerful device was born, an autonomous photo microreactor. During the day, it could capture sunlight directly. At night, it would run on solar energy stored in batteries, and a solar concentrator helped stabilize light intensity, ensuring the system continued functioning even in suboptimal conditions. The result? A breakthrough technology, a triumph of international collaboration. It's not yet a market-ready solution, but it stands as a powerful proof of concept, a significant step towards showing that we can do things differently, harnessing the power of sunlight instead of depleting the planet that sustains us.
The contribution of the Photo2Fuel project to achieve a climate-neutral Europe by 2050 is the development of a technology that has a very low technology readiness level now. So when the time comes, 25 years from now, we have more opportunities to implement it there. So we are not contributing only in turning light into acetic acid, but we are advancing science in several areas like the photosynthesizers, the photomicroreactor, the business models, understanding how the project impacts in the sustainability and in the market, so we can know how to move forward. Also, we are developing a roadmap for future research, so we advance into the implementation of such technologies, and then we can have more ways to deploy energy in the future, not basing only on fossil carbon. We can use sunlight and CO2.
The path was far from easy. Not everything went as imagined, and the journey is far from over. But this project has proven something essential, that when knowledge is shared, when people unite around a common purpose, even the boldest ideas can become a reality.
In Photo2Fuel project, we evaluate the end user perspective, which is fundamental to align with the market needs and the expectations from end users and stakeholders in the CCUS sector. While this is normally adopted for technologies that are well developed or nearing the TRL 9, it is something fundamental for technologies with a low level of development. It's not only for developing the technical aspects of the innovation, but also will allow us to align with environmental, sustainability, and societal aspects of the project.
8 organizations from 6 countries, people who didn't speak the same language, but shared the same vision. A small system with the potential to inspire something much greater. Living proof that alternatives are not only possible, they're already taking shape. And we're not just talking about science, we're talking about the future, about the courage to venture into the unknown, embracing failure as part of the process, and planting today what others may harvest tomorrow. Because if we are to build a cleaner world, a fairer world that is resilient enough to face tomorrow's challenges, then we need more projects like this, and more people with the courage to believe in them. This was Photo2Fuel, a journey of science, bound together by perseverance and collaboration.